Hello, this is a quick just overview of section 11.4, separation of variables. And the method of separation of variables works as follows. You put all the expressions containing the x values on one side of the equation, on all the expressions containing y values on the other. And clearly, if your variables in a problem are, for instance, p and t, that just means that one of the variables, all of the expressions are on one side of the equation sign, and in that case, the t's would be on the other side. And then you end up integrating both sides of the equation. Note that not all differential equations can be solved using this technique. It's basically a very nice one if you can get it to work, because the integration is usually fairly straightforward. And we can, in this case, look at an example where dy dx is equal to ky. So we separate the variables, and if we put all the y's on the left and the rest on the right-hand side, we're going to get 1 over y dy is equal to k dx. Notice that usually you end up multiplying and dividing both sides. Adding and subtracting usually gives you a problem. So use multiplication and division to do this separation. Now we take both sides of the equation and we integrate. So we get the integral from 1 over y dy is equal to the integral of k dx. And that implies that the natural log of y is equal to kx plus c. We technically have the constant of integration on both sides of the equation. But if you had an ln of y plus a constant 1 plus kx plus a constant 2, then we would just combine those. And so that step is kind of buried here. And we just have one constant of integration. It is extremely important to include that, because if you lose that, you basically are missing out on one of the parameters of the family of solutions. So bottom line, do not forget the constant of integration in this case, because it will give you a wrong answer. But having the constant of integration, we now take the equation ln of y is equal to kx plus c. We take the exponential function of both sides, and we get that y is equal to e raised to the kx plus c. Now remember your laws of exponents. That means that we can express the right-hand side as e raised to the kx times e to the c. And we can switch the order of multiplication. So we have e to the c times e to the kx. And e to the c, e to some constant, is just another constant. So if we relabel that and call that c1, we get that the solution is going to be y is equal to c1 e to the kx. So note that in solving the problem, you have to be careful. Multiply, divide to separate the variables. Then make sure that you integrate carefully and you put the plus c in there, and then the rest of it is a lot of algebra. This is example 2, where we're going to look at the h dt is equal to negative k times, in parentheses, h minus 20. A slope field is something that indicates what the derivative is at any time. And this can be used in kind of getting an image, kind of an idea of what that looks like just graphically, what the solutions will look like. In some semesters, I cover section 11.2, and some other semesters I don't. If this was not covered, then don't worry about it. The course will be adjusted so that you don't need to know this. To find the equation of the solution curves, or the answers, we separate the variables. And like before, you multiply, divide. So in the previous equation, you would take your h minus 20 and divide it over to the left-hand side. And you take your dt and you multiply that over to the right-hand side. So we're going to get the integral of 1 over h minus 20 dh. is equal to minus the integral of k dt. So we find then that by integrating both sides, we get the natural log of h minus 20 is equal to negative kt plus the constant of integration. Now, if you solve for h, then you get h minus 20 is e raised to the negative kt plus c. And just as in the very first example, we simplify the exponential equation by splitting that up into the product of two terms. So we get e to the negative kt times e to the c. E to the c is again just a constant. In this example, we chose to call it a. You could call it c1 again if you want to. And we would end up having that h minus 20 is plus or minus a e to the negative kt is b times e to the negative kt. So here we're dealing with the fact that technically we had the absolute value of h minus 20. That means that h minus 20 is plus or minus that constant e to the negative kt. But plus or minus a constant is still a constant, so we just change the name and call it b in this case. And next, we add 20 to both sides, and we get as a solution that h is equal to 20 plus b times e to the negative kt. And so b is a parameter. That could be a whole bunch of things. So if you choose b equals 0, you get h equals 20 as a solution. And if you choose b to be negative 10, then you get 20 minus 10 e to the negative kt. And these choices for b are kind of arbitrary. They are not having specific meaning except for kind of showing you what these solutions look like. So we have b is equal to 0 gives you h equals 20. B is equal to minus 10 gives you the curve here on the bottom. And b equals plus 10 will give you a curve here on the top. And so if you chose it to be plus 20, it would just come up, it'll be higher and then still kind of converge down to this solution of h equals 20. So a third example here, find and sketch the solution to the PDT is 2p minus 2pt, satisfying p is 5 when t is equal to 0. So this is an initial value problem. And that means we first find the general solution. We do the separation of variables on the differential equation. And then with the additional information that p of 0 is 5, we can figure out what that constant has to be for our particular solution. So factoring the right-hand side and separating variables, we're going to write that right-hand side as p times the quantity 2 minus 2t. And then we divide both sides by p, multiply both sides by dt. You're going to get dp over p is equal to the integral 2 minus 2t dt. Now you might ask yourself, could I have just factored out 2p and divided all of that to the left-hand side? Yes, you could. That would be a very similar solution. And in the end, after all the algebra, you'd end up with the same answer. When you are, however, setting up the separation of variables, the dp over p is going to be the ln of p again. And that's kind of a nice equation to have by itself. So in this case, when we integrate, we're going to get the ln of p is equal to 2t minus t squared plus the constant of integration. Now we solve for p, and we say that the absolute value of p is e raised to, well, everything that's on the right-hand side. So 2t minus t squared plus c. We can again split off the e to the c and write that e to the c as the constant a. So we get a times e raised to the function 2t minus t squared. And a is equal to e to the c, which is positive. A could be 0, gives a solution. And because we have the absolute value of P, we can again rewrite that whole thing as P is equal to B times e to the 2t minus t squared, where B can now be any number. It can be negative, 0, or positive. So to find the value of that B, we substitute in P equals 5 and T equals 0. So that means that 5 is B times e to the 0, which is B. So B is equal to 5. So our particular equation in this case to the initial value problem is P is equal to 5 times e raised to the function 2t minus t squared. So this graph can be provided as it's shown on the bottom of the slide here. It's a bell-shaped solution curve, and you could rewrite it a little bit and show that it kind of looks a little bit like the graph of y equals e to the negative t squared. Don't worry too much about, how you do that. You normally wouldn't be asked to do that on a test, but as a demonstration here, we wanted to show, and with we, I really mean the book, because that's where this example is pulled from, that this kind of looks like a y equals e to the negative t squared. And if you've taken any advanced statistics courses, you would know that this is the bell-shaped curve that is used in statistics. So this could be something that is related to something that looks a little bit like a normal distribution, although this would need to be scaled to be a normal distribution. But still, it looks like kind of a bell curve. And normally when you would do this on a test, you would go from finding the specific, the particular solution, the way it's given at the bottom of the slide here. You would be asked to graph this. So you would provide a graph like this with an indication of the scale, showing that it kind of starts at 5, has a bell curve that kind of comes back to the level where it started on the interval from 0 to about 2. So kind of indicating that scale would be useful. And that's it for the presentation.